So our next speaker is Julie Love. She is the product leader for quantum computing at Microsoft. She has a BS in physics from MIT and a PhD in physics from Yale University. And so, needless to say, she's super smart. As you all know from yesterday, I'm just a recovering politician, and when she explained to me what she was going to be talking about, I said what any politician would say. I said, "That sounds good to me." Anyway, please join me in welcoming Dr. Julie Love.
Thank you, Steve, and thanks to all of you for being here. This is my first time on stage in 2 years, and it's really fun to talk about the work that we've been developing over the last couple of decades and the last couple of years in particular. I need to move away from this. So Steve pitched this idea of talking about quantum computing and what it can change, and you're going to hear a lot of parallels actually from the last conversation. So unplanned, at least by me, but this is the brilliance of Steve and the organizers. Despite all of this power of the cloud that Mark talked about, the immense power that we've created for its computational capacity, there are still problems that are unsolvable by all of this compute power on the planet. Problems that are top of mind for a lot of the reasons that Mark discussed, but also thinking about the UN Climate Summit that's on our way this week. Sustainability, global energy production, global healthcare. And quantum computing is one of these technologies that some of us scientists and technologists are looking at to actually fundamentally advance the capabilities that we have for things like material science that Mark talked about. I started my career in quantum computing over 20 years ago with the first class MIT ever offered in quantum computing, and it's absolutely a dream to be talking about how we can make this technology real and practical and truly usher in this next revolution of technology. So as we talk about what quantum computing can change, I want to talk about this concept of a speedup and start there. So there's a maze of proposed applications around quantum computing. This is another area, to use another of Mark's phrase, that's prime for hyperbole. And as we talk about a speedup, what's really exciting, what gets us quantum physicists excited about quantum computing is it has a speedup, because these building blocks for a quantum computer work fundamentally differently than a classical computer. We're no longer working with bits, we're working with qubits. We can operate in this superposition state. We have quantum entanglement at our fingertips. And there are about 50 proposed quantum algorithms, or known quantum algorithms, with a proposed speedup, kind of a theoretically proven speedup relative to classical technology. So if you have n calls to, say, an oracle with a classical computer, you might be able to do it in square root of n calls with a quantum computer. Or maybe you have a cubic speedup, or even better, an exponential speedup. And so with this kind of maze of quantum algorithms that have been invented and proposed, there's a whole maze of potential applications that people have dreamt up using these algorithms. And so as technologists who are building this technology, it's really critical to understand, where are the promising paths in this maze and where are the dead ends. And so you can read about these quantum algorithms. These are maintained in the Quantum Algorithm Zoo, which is very appropriately named by my colleague, Stephen Jordan. And so as we look at this, because it really matters, we're building fundamentally different technology. It works very differently. We have to build a full compute stack. So it's really important that we understand what are the applications that are most promising and focus our energy and our work on those. So, and this comes in with some of the myths and misconceptions around quantum computing. Because of this, people are dreaming big with these speedups. I hear things like quantum computers are going to solve big data problems. So we heard about the immensity of the cloud, dreams of global weather prediction and climate models. Or things like, quantum computers are fundamentally faster because they solve exponentially faster because we're operating in superposition. And there's kind of hints of truth in some of these, but as we dig into it, to really understand what's going to be practical, we have to dig into where the speedup's going to be. And so our whole program and the work that we do is rooted in this concept of quantum practicality. We think that's the most useful definition. And this is a term that was coined about a year ago by my colleague Matthias Troyer at Microsoft. And he defined quantum practicality as being able to solve a problem that's useful, either to scientists or in technology, to be able to do this faster than any known classical algorithm and any known, the best classical computer. And so everything's on the table. Special purpose silicon designed to do specifically one thing. And if we're really going to say quantum is practical speed up against that, we have to compare against everything, the best known classical methods and any special purpose classical chipset. And then from a practicality perspective, as you look at this zoo of quantum algorithms and applications, some of these still, we're up against classical workloads. So if we think about inventing and designing a new catalyst, it may take us longer than the lifetime of the universe with conventional computers. But sometimes if the speed up's not enough, the quantum algorithm is not that much faster. And so we want to do this practicality comes in at human time scales too. We want to have this speed up in human time frames. So, days, hours or days ideally, but certainly not more than a few weeks. And so as I have this plot here with time on the vertical axis, which is a little wonky for physicists. We don't usually plot time that way. But crossover time versus problem size. And so as this problem size n, as that goes to infinity, we can physicists love to look at the edge cases of things. So as n goes to infinity, which is a standard thing for a physicist to say, quantum computers, as long as you have that speed up relative to classical, the quantum computer is always going to win. It could be billions of years, but it's going to win. And on small problem size, when n goes towards 0, the classical computer is always going to win. The compute power that we have on our phones and our laptops, probably my watch, for small problem size, the classical computer is always going to win. And so it's really this crossover point that things get interesting. When do we get this practical speed up in a human-sized time frames for really, for interesting and really economically viable problems? So I'll do a little comparison. And I'm benefiting from the use of slides, even though it's maybe not. So as we do this comparison, I'm going to have this rigorous comparison between classical chipsets and I'll say tomorrow's quantum computer. So we'll be a little bit optimistic. And as we do this, so we don't miss any potential quantum applications, I'm going to be, in this comparison, I'm going to be pessimistic on the classical chipset. So I'm going to compare it to a chipset that we have today. We're continuing to advance, but we're seeing the slowdown, if not the end of Moore's law. And I'm going to be optimistic on the quantum computer, so we don't miss anything. So I'll compare with a GPU chipset. We'll take the NVIDIA A100 GPU. It has about 54 billion transistors and a little bit less than a nanosecond of cycle time. And we'll be a little bit optimistic on tomorrow's quantum computer. For those of you who have dug into quantum computing, we'll assume all-to-all connectivity, so we don't have to worry about shuttling qubits around and losing time because of that. I'll look at a quantum computer of about 10,000 logical qubits, and I'll assume a 10 microsecond cycle time. And so this is logical operations. I don't have time to get into the details of logical versus physical operations for a quantum computer, but we need to have some method of error correction. And so this is logical operations that are coming through, say the algorithmic layer versus the physical operations. And so as we look at this, so we talked about the concept of a quantum speedup. So quantum computers, because they have this speedup inherent in the algorithm, this is what those algorithms are famous for, they don't need as many operations as classical computers. So that's kind of the starting point. So we don't need as many operations. But as we look at these different time scales of operation for these systems, they're orders and orders of magnitude slower on the quantum computer. So the colleague that I showed you the picture of before, he would say, quantum computers can solve everything, but it's going to be billions of times slower on average than your classical computer. So great, that's a great starting point. So I'm going to start at the bottom because I started with that myth about big data. So as I'm going to take the bottom of the chart and just look at the read rate. And so this A100 GPU reads in data at about 10,000 gigabits per second. And so these are some of the scales that we heard about in the last discussion. The quantum computer is going to read in data 10,000 times slower than that, so about a gigabit per second, optimistically. So already I've got a factor of 10,000. So as we think about these big data workloads that people come to us and say, hey, we want to use the quantum computer for this, even if we have the algorithmic speedup for the quantum computer, we're going to lose on the read rate. We're not going to be able to read the data in fast enough, and the classical computer is going to win, kind of in the relevant timeframes. Now we look at the kind of clock rate and logical operations. So as we look at logical operations, we've got these GPUs operating at 5 petaops per second, or even faster with a special purpose ASIC. And the floating point operations, we're looking at teraops per second. And so now you look at this difference between the classical computer and the quantum computer. So now I've got petaops versus megaops, or even worse for the floating point operations, kiloops. So as we look at this, this is really helpful as we look at that zoo of application areas. So we can start to narrow things down. So there's 2 big conclusions for this without going too much into the details of how these systems work. So quantum computers will excel at big compute problems. So these are not big data, but big compute problems, where there's so much information we're compute bound on small data sets. And I'll talk a little bit more about what these problems look like. And also, we need that speed up to be more than quadratic, super quadratic speed up, because we have to overcome those time scale differences, orders and orders of magnitude slower clock speed. But we can do that if we start to get towards more exponential speedups rather than quadratic. Quadratic isn't going to cut it. Cubic starts to get us there, but higher power speedups start to get us there. So we have invested much of our program in really understanding what are these application areas that are going to advance the state of the art for technology, these leadership class applications. And so we can look at that. We have incredible tools for resource estimation. So even though these quantum computers that'll solve these problems don't exist yet today, we've created powerful software tools that allow us to estimate the resources consumed by these algorithms. So we can count the number of qubits that's required, and we can know how many operations it's going to take, and we can do that algorithmic work today. And as we look at these problems and then benchmark them to practical quantum computers, being, again, really optimistic on what the quantum computers can do, we start to see interesting applications that drive the state of the art of scientific understanding. So quantum magnets and things that are interesting from the academic community. And when it starts to get really interesting is when we start to see leadership class solutions coming in the millions of qubit range. And I totally unplanned this discussion about material science that happened right before this. This is exactly where we're going to see this revolution for quantum computing. So computational chemistry and material science, where there's so much information due to the quantum nature of chemicals and materials. There's so much information contained in those systems that classical compute can't keep up. This is exactly at the heart of where this revolution is going to come from in quantum computing. And before I skip to the next slide, this is sort of a boring PowerPoint slide with a chart, but I mean, this is really exciting. This is practical quantum computers that exist, quantum applications and quantum algorithms that exist for really meaningful, powerful things in our economy. So let me give you an example of what one of these problems could be. So also in honor of the UN Climate Summit happening right now, Microsoft is taking significant pledges in our carbon footprint and really creating a community around us to do the same. And this is one of the questions that we put to our research team, is to say, can we, with the future quantum computer, use quantum algorithms and quantum hardware to design a chemical process that could remove carbon from the atmosphere, solve this carbon fixation problem? The challenge in this is catalysis, again, what we heard about from this morning. The challenge here is having an efficient catalyst to remove carbon from the atmosphere. So there's been lots of proposals for catalysis in this space. But an efficient catalyst is one where you have carbon dioxide coming in, it interacts with a catalyst, and a catalyst is driving a series of chemical reactions efficiently. And what makes this really hard to design these catalysts is that you have to very accurately know the energy levels of the intermediary states as you go through this cycle. to get something that's efficient and doesn't use up the catalyst in the process. And so an efficient catalytic reaction is one where we're going to get, you'll see the same catalyst coming out the other side, and actually an economically viable material coming out with it. And so these catalysts have been proposed as a ruthenium-based catalyst, and it could spit out methanol, which would be economically viable as well. And so getting this efficient catalyst is really hard to design because with classical computers, we can't get the accuracy and the energy levels that we need to have this be efficient. And so the way that this is done typically today is we get as far as we can with classical workloads, and computational chemists propose catalysts. But then to know if this is going to be an optimal solution, they have to be tested. They have to be manufactured, tested. This is a lot of wet bench chemistry. And as we look at these catalysts that are designed, the one for synthetic nitrogen fixation to produce artificial fertilizer, 10,000 cycles of this to get something that was viable. So incredibly expensive, incredibly time-consuming. And so as we think about speeding this up, this is the promise of quantum computing. Quantum computer is not going to be a standalone workload. It's going to be a hybrid workload. And so it's going to coexist with state-of-the-art leadership class, high-performance computing systems. And so this now introduces the opportunity to radically accelerate this innovation cycle. So we have, sorry, these words are really hard to read on the screen. I can kind of walk you through it. So we'll use the classical workloads to explore and propose structures. Then we can send that as a subroutine into the quantum system and get those really accurate properties using the quantum computer that we can't get from the classical computer. And then feed back that information. This is certainly going to rely on machine learning and artificial intelligence layered onto this. Now we have a really powerful R&D cycle that allows us to get much closer to something before we go and test it in physical systems. The implications of this are massive. So as we've looked at this just over the past few years, so 2014, we took our first cut at the algorithm for this. Like I said, the devil's in the details on these speedups. And so our first cut at the algorithm was down from the lifetime of the universe to a mere billion years on the quantum computer. It's life extension aside, not super practical for the health of our planet. In 2017, we had that down to 100 years. So we're chipping, we can do the algorithmic work and design these algorithms to run more efficiently. It's going to be a really multidisciplinary approach, people who know how to write good, fast code. So we've chipped away orders of magnitude. And using what we know about state-of-the-art classical workloads and being able to pair this together, we now have an algorithm that will run in a month when we have the right size and quality of quantum computer. Here's a few other examples of where this comes in. I think after the morning's talk, you won't be surprised that advancements in chemistry and material science have potential to really advance the state of the art. So here's a few other areas which we see potential for in quantum acceleration. So the first is around clean combustion. Can we design catalysts that would remove byproducts from combustion, nitrogen oxides from the system? And clean energy, we can think about, I talked about carbon fixation, massively deploying that, or improving, having materials that have better, energy capture from photoactivation and photovoltaics. We can think about clean water as we think about more broadly looking at sustainability. Catalysts that would improve, removal of bacteria from water, more efficient than titanium dioxide, which is used today, or something that could remove VOCs on the surface of water. As we think about energy efficiency, we think about, could we use this technology to design a superconductor a material that superconducts at higher temperature? If you think about the economic implications of that, we lose about 15% of all electricity generated in our grids just through losses in the material. And so as we look at this maze, it's really, really exciting and inspiring. This is, especially on the carbon fixation, this is what keeps me fired up and coming to work every day and building this technology. And even if these, as we looked at that whole maze, as we started out this discussion, that whole maze of potential applications, even if these are the only ones out of that maze, Even if these are the only ones, it truly changes everything. We're looking at significant economic and productivity disruption. And so this is the focus at Microsoft is saying, okay, we have these opportunities to go change everything. How do we build this? So big part of quantum practicality is building a system that can actually go address these workloads. And so we also have some rules around what it's going to take to build a system to achieve quantum answers to these solutions. And so quantum practicality requires us to have qubits that are highly manufacturable. We operate the qubits at millikelvin temperatures. And so we're building a full compute stack in this environment. Millikelvin temperatures, maybe not everybody's calibrated in millikelvins. It's about a few hundred times colder than deep space. So we're operating these really, really cold so we can protect the quantum information. But we've got to have these really small so they can sit on a single module. The heat capacity of these systems, the cooling power, we call them fridges, of these fridges that we put these systems in is really, really low. So we need to have something that'll sit on a single module so that we can have this, things like all-to-all connectivity of the qubits. And then we need a scalable readout and control strategy. It's going to take a supercomputer to control and read out the quantum computer, all of this information processing. We've got to have speed. So going back to those time scales, we've got to have fast gate speed so that we can have these applications run in human relevant time frames. If that clock speed goes down, you can just tack on more orders of magnitude in terms of the speed up that you require. And then we need reliability from the qubits. So I glossed over it a little bit, but I kind of talked about the number of physical qubits that we need in my chart versus logical operations. And the higher the error rate is, the number of physical qubits that you need explodes. And that makes this, it's going to be a really challenging engineering problem to assemble the system that can operate that cold, that fast. And so these are really the constraints around building a quantum system that'll satisfy this need for quantum practicality. So I won't have time to dig in too much to this, but we're working on a really fundamentally different type of building block for quantum computers, even though they're all pretty fundamentally different than what we're used to today. And we're building our system with a building block of topologically protected qubits. And so the field of topology is, I guess because of COVID, we don't have any coffee cups on the tables, but the topologist will tell you that the coffee cup is the same as a donut because you can morph one into the other without changing its fundamental property, which is that hole. And so topological materials are unaffected by noise in the environment. That information is protected. We encode the quantum information into the material itself to have that low error rate. And they satisfy all these requirements that I shared on the last page. And the control system also matters. So if those of you who've been watching the field, standard control systems to control, say, about 100 qubits, this is a system that would control about 100 qubits, is you see this kind of bird's nest of wires. That's not going to scale into the tens of thousands to millions of qubits and maintain the protection of the qubits at these ultra low temperatures. And so we're also working on that and advancing the state of the art of control. So what you see here is a picture. It's kind of deeply embedded, and there's this orange speck in the middle of that picture. We're working on cryogenic control systems. And so we've got to advance classical state of the art to be able to control and read out these qubits. And so these are systems, this is a system that can control up to 50,000 qubits at millikelvin temperature, needing only 3 wires up to room temperature. And the other part of practicality is making this available in the cloud. This is a hybrid workload. And we want, as I talk through this concept of carbon fixation, it really is time to advance and get started on this technology now. It's going to take time for us to develop the algorithms and develop the expertise and really the intuition around programming in this really different way. And since we were bringing all this technology to Azure, we're putting it in the cloud. This is a hybrid workload. This is the natural place for this to be. For developers, innovators, scientists to come build their quantum workloads here. We've completely open system. We've embraced all of the leading Python frameworks. Integrate these workloads with the classical architecture. This is going to, advancing the state of computational chemistry is going to require us to be tightly coupled with high performance computing and the state of the art with classical technology. And these are integrated workloads. testing the code. Testing and debugging looks really different when you're working in superposition. Resource estimation, the algorithmic work, so you can test and debug, and then run on the latest quantum hardware. And we're doing this in a very open way. This is the same quantum code. It's sort of the dream of write once, run everywhere. So we've brought in leading quantum hardware from our partners IonQ, Honeywell, and QCI. We'll be introducing our topological qubits into this. And really this open cloud ecosystem. And I'll tie once more back to Mark's talk this morning. This is a general purpose system. And with general purpose system, I truly believe what Mark said. We just don't know what people are going to do with it. It's time to get started. We hope that you and your teams will join us. You can get access to all of this in Azure today. And for those of you who are running research teams or connected with academic groups, we're also giving away credits to put this in the hands of researchers who are going to discover new and innovative things to do with this technology. This really is going to take a global community to build and realize the potential for this, and we just can't wait to see what people will do with it. Thank you.
Great, thank you. My name is Alvin. I'm kind of like a Teal disciple, so sorry if I come at you a little bit hard. Yesterday he mentioned in 2010 sort of the artificial intelligence, super AGI promise of DeepMind and OpenAI. This sort of seems like the same thing where you just do this magic computer and watch the future unfold. Where is the progress really? I've been tracking quantum computing for about 5 years. I still don't really see all these things unfold. Are these just like future things that we wait for, or is there actually some things being done?
Great question. But there have been absolutely fundamental advancements over that. I'll take the 5-year period that you mentioned. In terms of building the systems, we've been working on this for about 2 decades at Microsoft. And the ability to manufacture the materials and the systems to be able to exhibit these properties, it's been fundamental challenges in physics. New physics discoveries have come about and are required to realize this technology. And we've made incredible advancements. I shared a couple of them actually. In terms of the algorithmic work on carbon fixation, that's been a fundamental advancement. The cryogenic control systems required to be able to scale. So our program, I can only speak to our program, has been rooted in this notion of practicality, really. So advancing all of those layers of the stack. And it's going to take more engineering advancements to get there. But it really is truly a time when, actually 2 years ago, probably this week, what is it? The 11th? I think 2 years ago, maybe on the 12th, we were on stage at Ignite and Satya Nadella announced Azure Quantum. And we have people using this system every single day and advancing the state of the art. We have quantum computing in the cloud, in Azure. And so for me, it's pretty exciting. And the other thing I'd say, I wasn't at the talk last night, but as we look and measure progress, I think the human, maybe some of the futurists in this room are more tuned into exponential growth, but I think the human brain doesn't comprehend exponentials very well. And so as you look at technologies that really accelerate exponentially, and quantum will be one of these technologies, it always looks slow at the beginning. If you look at the shape of an exponential, it always looks slow. And when you double, you're still kind of on the flat part of the curve, and you double again, and you double again. And then you get that exponential. And so, we've seen that. The past, these past technical revolutions have also been exponential. So I'm really excited. I'm really excited and optimistic about what we're building and the potential of this technology.